Hey, what's going on, guys? Let's look at this problem right here. Here this question is asking, write the negation of each of the following propositions. Determine which is true, the proposition or its negation. Here we have the proposition, for all x belongs to real number, x is less than or equal to x. If we write the negation of this one, whenever we have for all, the negation of this one is going to be there exist. So this is there exist and x belongs to real number such that this will, whenever we have greater than or equal to, that will be opposite, less than x. Okay, now which one is true? For example, if I grab 2, can 2 be greater than or less than 2? Right, it cannot be, right? It can be equal to 2. It's equal to 2. So this one is correct. The proposition is true. So we can say this is true. The proposition is true. Now let's look at another one. Here this one says there exists an x belongs to real number such that x square is less than 0. If you write the negation of this one, the there exist will become for all x. So for all x belongs to real number such that x square, this one turned into opposite, greater than or equal to 0. Now let's try some numbers. For example, if I try 1 square is equal to 1, 2 square is equal to 4, 3 square is equal to 9, and 0 square is equal to 0. So here this x square is never greater than 0, right? It's never less than 0. It's always greater than 0 or equal to 0. So this one seems correct. This one is correct. The negation is true. Negation is true. Now let's look at another one. Here it says there exists an x belongs to real number. For all y belongs to integer, x is less than or equal to y. If we negate this one, there exist will become for all. So this is going to be for all x belongs to real number, and for all y will become there exists a y belongs to integer such that x, and this will become opposite sign, greater than y. Okay, now let's look at which one is going to be true. Here it says there exists an x belongs to real number. For all y belongs to integer, x is less than or equal to y. So here it says there exists a real number. So whatever the number is, for example some number, it's less than all the integers. Is it possible? It's never possible, because no matter whatever number we pick, there's always a number less than that, right? So this one is not true. Now let's look at this one. For all x belongs to real number, there exists a y belongs to integer such that x is greater than y. Okay, so here if we pick this one is correct, because here we are picking up a number. They're saying for all real number there exists a y belongs to integer. For example, if I pick 2 such that x is greater than y. So if I pick another number like 3, it's bigger than 2, right? So this one is correct. Here the negation is correct. Negation is true. Now let's look at this one. For all x belongs to integer, there exists a y belongs to real number such that x is less than or equal to y. If we negate this one, for all x become there exists an x belongs to integer, and there exists a y become for all y belongs to real number such that x, this will turn opposite, greater than y. Now let's look at some examples. For all x belongs to integer, there exists a y. Okay, this one looks like the previous one. Here they are saying for all integer there exists a real number such that x is less than or equal to y. This one is correct, because there exists, we are like trying to compare. For example, the same example applies to this one too. If we pick up 2, 3 is greater than that, right? So this is always true. This one is correct. Now let's look at this one. There exists an x belongs to integer. For all y belongs to real number, x is greater than y. So here there exists an integer. For all y belongs to real number. So there cannot be a number, integer number can be greater than any real number, right? It cannot be true, because there's always something bigger than that. So this is not true. So here the original proposition is true. So this one is true. Now let's look at next one. Here it says for all x belongs to a rational number, there exists a y belongs to rational number such that xy is equal to 1. If we negate this one, for all become there exist an x belongs to a rational number, and there exists a y become for all y belongs to rational number such that xy, if it's equal, it will become not equal to 1. Okay, here it says, let's read this one again. For all x belongs to an integer, there exists a y belongs to integer such that xy multiply equal to 1. Can you find a number, two integer number, when you multiply, like here, like for all integer, for example, if I pick 1.5, this is a rational number, so if you multiply a rational number, that will give you 1. Can you find a number, such number like that? It's not possible, right? So here, this one, the negation says there exists an x belongs to rational number for all y belongs to rational number such that xy is equal to not equal to 1, because if you multiply two rational number, you will not get 1. So that's correct. So the negation is true. The negation is true. Now let's look at the next one. Here it says there exists an x belongs to rational number for all y belongs to rational number such that xy is equal to 1. If we negate this one, there exists become for all x belongs to rational number, for all y become there exists y belongs to rational number such that xy, if it's equal, this will become not equal to 1. This is same as the previous one. Here it says for all x belongs to rational number, there exists an x belongs to rational number for all y belongs to rational number such that xy is equal to 1. There you cannot find a rational number like that, right? So it's not possible. Here it says for all x belongs to rational number, there exists y belongs to rational number such that xy is equal to not equal to 1. This is true. So here the negation is true. Negation is true. And that's how we do that. And if you are trying to learn discrete mathematics, there are a bunch of videos in my playlist. I hope you guys watch that too, and don't forget to subscribe. See you next time.